All right, so once again, we want to solve this higher order equation. And to do so, we start off with the auxiliary equation, which again is a polynomial. So it's going to be an r to the third power minus 10 times r squared plus 37r minus 52 is equal to 0. And unlike the other problem where we could factor by grouping, grouping is never going to work on this problem because you could never find common factors between 37 and 52. So instead, what we're going to do is turn to our graphing calculator and graph this cubic polynomial and get a root from that. So if we graph this on our calculator, just by entering it into y equals, and you'll notice that the graph is going to cross visually at r is equal to 4. And the graph of this is just going to be a polynomial that kind of comes down like this. And again, this looks like 4. And you could use the root feature or the solution feature of your calculator to find this. But again, visually, we could pick this one off pretty easy. Sometimes you may have to use the root feature if it's a fraction, which is possible as well in some of these problems. So if we have r equals 4, we can now use synthetic division to divide the 4 into the coefficients of the polynomial, which is 1, negative 10, 37, and negative 52. Again, bring down the 1 and multiply to get 4. We add to get negative 6, multiply to get negative 24, add to get, looks like 13, and then 4 times 13 is 52. So we have a remainder of 0. So we know that R1 is equal to 4. All right, next up, we have a resulting polynomial, which is r squared minus 6r plus 13 is equal to 0. Again, we could use either the quadratic formula, but again, I like to complete the square because it has an even coefficient in the middle. So that's an r squared minus 6r, bring the 13 over as a negative 13. Taking half the negative 6, that's negative 3. Negative 3 squared is 9. So we're adding 9 onto both sides of the equation. This factors as r minus 3 squared. And that's equal to a negative 4. If we take the square root of both sides, this gives us r minus 3 equals plus or minus 2i. If we then add the 3 to both sides, our r is equal to positive 3 plus or minus 2 times I. And that gives us our other two values of r, a complex conjugate pair. So now our solution, as we saw earlier, is going to be a linear combination of the terms that we get from using these as our exponents. And again, complex numbers turn into sines and cosines. So we're going to have a c1 e to the 4t, and then a c2 e to the positive 3t cosine of 2t, and then a c3 e to the 3t sine of 2t. And again, the idea is that even though we saw complex numbers in our process, we get a real valued solution for our differential equation. So that is the solution of this third order equation. Again, you could either use the Wronskian or make an argument about the constants to show that these terms are linearly independent.